we said that if the process is reversible, then entropy change would happen because of heat transfer. So what does the expression 2 tell you? The expression 2 tells you that if the process is reversible, okay, then the entropy change can happen. It can change if there is a heat transfer del Q. If there is a heat transfer, okay. So if there is no heat transfer, if there is no heat transfer, then this, and if the process is reversible, then the ds would be 0. Okay, you can substitute the value of del Q as 0. You can substitute the value of del Q as 0 in the expression, and you would get that ds is equal to 0 if the process is reversible. It means that the entropy would not change if the process has no heat transfer. If there is no heat transfer, then the entropy would remain constant. Okay, this you need to keep in mind. Now we had then derived an expression for entropy change during an irreversible process using our Clausius inequality, and we went on to show that the change in entropy for an irreversible process would be greater than the change in entropy for a reversible process. Okay, between the same two end states. So between the same two end states, if you are talking about the change in entropy, one for a reversible process and other for an irreversible process, then the change in entropy during an irreversible process would be obviously greater than the one where if the process was reversible. And this was captured in expression 3. This was captured in expression 3, that the change in entropy. So if you look at expression 1, the change in entropy for an irreversible process is greater than del Q by T. Okay, del Q by T reversible. Okay, so the difference in expression 1 and 2, the difference in expression 1 and 2 has to be because of the irreversibility, right? So why is that the expression 1 greater than expression 2? Okay, so if you look at expression 1 and expression 2 carefully, why is that expression 1, the entropy change is greater as compared to the one in expression 2? Okay, so the reason is the entropy change expression 1, okay, which is given by the equation 1, that is more because of I, and this I is irreversibility during the process. Okay, so one can say that there is change in entropy, because of irreversibility, and there is change in entropy because of heat transfer. Okay, so let me write down very clearly. Okay, let me rub this, and let me write down that why the entropy changes during a process. Okay, so the entropy would change. The entropy would change. Let me rub this. So the change in entropy, during irreversible process, okay, would be because of change in entropy, because of heat transfer, because of heat transfer, and and also because of, and also there would be change because of irreversibility. Okay, so there are two reasons. You see that these two reasons would have resulted in the change in entropy during an irreversible process. Okay, so one can say that transfer, there is a change in entropy. So what we would be doing is that we would be now using a term. To differentiate between the change in entropy because of heat transfer and change in entropy because of irreversibility. So let me use a term called entropy transfer. Okay, and I will be explaining you this shortly. Let me use a term called as entropy transfer. Okay, let me rub this first. Okay, so now you only one expression is left in front of you, that is the expression for change in entropy during an irreversible process. Okay, so I have now broken that expression into two parts. One is change in entropy because of heat transfer, and other is change in entropy because of irreversibility. Okay, so I will call this as change in entropy because of entropy transfer. Okay, entropy transfer. Now let me elaborate on this first. So suppose you consider that there is a closed system. Okay, suppose you consider that there is a closed system, and this closed system, let us say, receives certain heat, and this heat is received reversibly. This heat is received reversibly, okay, from certain source of heat, and let us say that this source for the time being is an imaginary source whose temperature remains constant at T. Okay, constant at T. And if this heat transfer is reversible heat transfer, if the heat transfer is reversible heat transfer, then the boundary temperature would also be almost T. Okay, the boundary temperature at which the heat transfer happened, this boundary temperature will be also almost T. Okay, almost T, not exactly T, because you need to have an infinitesimally small temperature difference. Okay, so now what would be the change in entropy during this? So the change in entropy during this process, would be del Q by T. Okay, or let me write down, not for a infinite actual entropy during this process would be integral of del Q by T. Okay, which becomes equal to, because this is a reversible heat transfer, and this heat transfer happens at constant temperature, because we are talking about the reversible heat transfer at a source temperature. So I can take this T outside the integral. Okay, so this becomes Q upon T. Okay, if you solve this integral, you get Q upon T. Now what is this? So this is a change in entropy. This is the change in entropy. And why has this change happened? This change in entropy has happened because of a reversible heat transfer, okay, at the source temperature, okay. And this change in entropy, physically, if you want to see that why has this entropy of the closed system increased, this is because of this heat transfer, the molecular disorder would increase. Okay, the molecular chaos would increase because of the heat transfer, right? So one can say that along with this heat, there is entropy. Along with this heat, there is a entropy transfer. Okay, along with this heat, there is a entropy transfer. So please note that whenever the system accepts the heat, the entropy would flow into the system. Whenever there is a heat transfer from the surroundings, this is the surroundings to the system, there will be entropy transfer to the system, as a result of which the entropy of this closed system would increase. Right. So entropy transfer is essentially associated with the heat transfer. So change in entropy because of entropy transfer happens because of heat transfer. And why is that there is a entropy transfer associated with the heat transfer? Because along with the heat because of the heat transfer, there would be a change in the molecular disorder. Okay, and that molecular disorder, you know that it is captured by this term called as entropy. Okay, so please note that one reason for change in entropy is the heat transfer, and we can say that this entropy has changed because of the transfer. Right. Now what if the system was rejecting the heat? So let us take a case now. Of a closed system, and let us say this closed system is rejecting certain heat to the surrounding, and let us say that it happens at certain temperature. Let me differentiate this as TH, and so this would be TH almost, and then this would be TH almost, and this would be almost TH, and this would be almost TH. Okay, right? Now this heat is being transferred to the surrounding, which is, let us say, at TL, and let us say that heat transfer is reversible heat transfer. Heat transfer is reversible heat transfer. Okay, there is a reversible heat transfer now, but what is the difference between this case and the earlier? The difference is that this reversible heat transfer has happened in the opposite direction. That is, the system is losing the heat. System is losing the heat. Okay. So now if the system is losing the heat, what would happen to the entropy change of the system? Okay. So the entropy change of the system would be integral of del Q by T. Integral of del Q by T. And because the heat is through the surrounding, I'll put a negative sign. I'll put a negative sign. Right? And because the temperature is constant and it is TL, so I can take this temperature outside the integral. So it will be integral of TL and minus del Q. Integral of minus del Q, which comes as Q upon minus Q upon TL. Minus Q upon TL. Okay, so if I call this as an expression 2 and this as equation 1. Okay, if you compare this two, so in both the cases the entropy change is captured. Okay, but now in the case 2, what you will find is that the entropy is decreasing. The entropy of the system is decreasing. Entropy of system is decreasing. Are you getting this? Entropy of the system is decreasing. Why is the entropy of the system decreasing? Entropy of the system is decreasing because there is a heat transfer, there is a reversible heat transfer from the system to the surrounding, as a result of which the molecular disorder would decrease in the closed system and the entropy of the closed system would decrease. So along with the heat flows the entropy. So when the heat flows outside the system, okay, when there is a heat transfer from the system to the surrounding, the entropy also flows along with it, along with this heat, as a result of which the entropy of the closed system would decrease. Okay, so along with the heat flows the entropy. Okay, this is one of the important point you need to note down. Okay, so the part first of this expression, that ds irreversible is ds heat transfer plus ds irreversibility. So the first part of the equation is the entropy change because of heat transfer, and this entropy change can increase or decrease. Okay, the first part of the equation can be positive or negative depending upon the direction of heat transfer. Okay, so the entropy change would be positive. This first part of the equation would be positive if the heat flows into the system, because along with the heat flows the disorder, along with the heat flows the entropy, right? And this ds would be negative if the heat flows outside the system to the surrounding, right? Outside the system to the surroundings, because then heat flows out, the entropy would flow out. So entropy transfer happens from the system to the surrounding, as a result of which the entropy of the closed system would decrease, right? So this is one important thing you need to understand, right? The other important thing you need to understand is now that the entropy change of the irreversible process, okay, would also be because of the irreversibility. So what are the irreversibilities we had discussed? So one could be the irreversible heat transfer, other could be friction, etc. Okay, so whatever are the irreversibilities, okay, these irreversibilities are going to increase the entropy. Mind that irreversibilities are going to increase the entropy, right? So I am using the term that because of the irreversibilities, the entropy would be generated. So I am now using the term entropy generation, right, to account for the increase in entropy because of irreversibilities like friction, etc. Okay, so two things you need to keep in mind: that change in entropy during an irreversible process is because of the heat transfer and because of the irreversibility. The first term, the change in entropy because of heat transfer could be positive or negative depending upon the direction of heat transfer. If there is a heat flow outside the system, the entropy would decrease. If there is heat flow into the system, the entropy of the system would increase, right? The second term is the entropy change because of irreversibility, and this is irreversibility, right? So this irreversibility would always lead to increase in entropy, would always lead to increase in entropy. So this term is always positive. Please note this is always positive, and this is the generation. This is the entropy generation. So in a way, we can now figure it out that entropy change, okay, is in during an irreversible process is a summation of entropy transfer plus entropy generation. Entropy transfer plus entropy generation. Okay, now look at the first question which I had given you. Let me close this down. Let me rub this all. Okay. Let me discuss the question which I had given you in the poll. I had talked about the reversible heat transfer. I had talked about the reversible heat transfer. Okay, which is isothermal. Which is isothermal. So I had purposefully taken a process which is the process of a Carnot engine. Carnot engine. So let us say that this is the system. This is the system, and there is a heat transfer. There is a heat transfer to the system, and this heat transfer happens isothermally, okay, at constant temperature, which is equal to the source temperature, because it is a reversible heat transfer. Okay, so in this case, what would happen to the change in entropy? So the change in entropy during such a process is given by integral of del q by t from some initial state 1 to the final state 2. Final state 2, and if the temperature remains constant, I take this outside the integral, and this would be from 1 to 2 del q, which is nothing but q during the process 1 to 2, in the process 1 to 2 upon t. That is the heat transfer upon t. This is the expression for entropy change. Entropy change, and we are writing the entropy change for a reversible process. Okay, so what I said is that when there is a transfer of heat to the system reversibly, the entropy, because this is a positive value, because you are talking about the heat transfer to the system, so the entropy change would be a positive value. Okay, the entropy change would be a positive value. In other words, the entropy 2 would be greater than entropy 1, or there is an increase in entropy. There is an increase in entropy in spite of the fact that the temperature remains constant. Okay, temperature remains constant, but the entropy increases. So if you remember the temperature entropy diagram for a Carnot cycle, this can be represented as a horizontal line away from the vertical. Why is that so? Because the entropy at 2, this entropy would be greater than the entropy at 1. And why has that happened? This has happened because of the heat transfer. This has happened because of the heat transfer from the surrounding, which includes the source, to the system reversibly. So the temperature is constant, that is T1 would be equal to T2, which will be equal to the source temperature. Okay, almost source temperature, and the entropy would increase from S2 to S1, S2 to S1. Okay, so this you need to keep in mind. In the reversible heat transfer, which is isothermal, the entropy would increase, and it would not remain constant. What if there is a heat rejection? What if there is a heat rejection? So in that case, if there is a heat rejection, one can show delta S in such a reversible heat transfer case would be minus Q. Let that process be 3 to 4, for example, upon T. This can be shown. Okay, and that can be represented on the TS plot as like this, that it's an isobaric process because the temperature is constant, it would be a horizontal line, and the entropy at 4 would be less than the entropy at 3. Entropy at 4 would be less than entropy at 3. In other words, the delta S would be negative. Delta S would be negative. And why has that entropy decreased? The entropy has decreased because the heat has flowed away from the system. So if there is a heat flow away from the system, okay, process 3 to 4, if there is a heat flow away from the system to the sink, okay, which is at TL, okay, which is at TL, which is equal to 3 is equal to T4, then because the heat is thrown out of the system, along with the heat, the entropy would also flow out, and the entropy of the system would decrease. Entropy of the system would decrease from S3 to S4. Entropy of the system would decrease from S3 to S4. The change in entropy during that process would be negative. It would be negative, right? So this you have to be very clear. This you have to be very clear, right? Now, what if the process is irreversible? What if the process is irreversible? So, if there is an irreversibility, then there could be. Now, let us take an interesting process. Okay, let me and let me before going to irreversibility, let me discuss another process, which is a reversible adiabatic process. Let me discuss an interesting process, which is a reversible adiabatic process. Okay. Reversible adiabatic process. Okay. Now, what is the adiabatic process? Adiabatic process is a process in which the heat transfer is zero. So the heat transfer would be zero. Let us say some process 2 to 3. So if the heat transfer during the process 2 to 3 is zero, right? Or any process 2 to 3, A to B, whatever, then that process is an adiabatic process, and we are discussing a special case of reversible adiabatic process, right? So in this case, what would be the expression for entropy change? So you know that expression for entropy change for a reversible process is del by, okay, and because this is a adiabatic process, this term is zero. This term is zero. So it follows that ds, if you substitute 0 in place of del q, so del ds reversible will be equal to 0. Let me put 0 here, right? And it means that s is equal to constant. S is equal to constant. Okay. Or in other words, entropy is constant. Entropy is constant. Okay. So the entropy is constant. We can use another term for the process, isoentropy. Isoentropy means isentropic. Isentropic. Okay. So note that. Look at this isentropic. So if the process is reversible, right? So the process is reversible, the entropy cannot change because of irreversibility, and because the process is adiabatic, there is no heat transfer to change the entropy, because along with the heat flows the entropy, so there is no heat transfer, not be any flow of the entropy, and hence the entropy of the system would remain constant. Okay, so please note that when the process is reversible adiabatic, the entropy would remain constant. And if I want to represent this process on a temperature entropy diagram, then that representation would be a vertical line. That representation would be a vertical line. Why it would be a vertical line? Because the entropy is constant and the temperature would drop if there is a expansion, for example, in the Carnot cycle. So in the Carnot cycle, you know that these are the two processes which are important, wherein the entropy remains constant, and both these processes happen to be reversible adiabatic processes. As a result of which the entropy remains constant. Okay. So this you need to keep in mind. Let me ask you these questions again, if you are really following this or not. let me ask you, the poll is open. Let us see how many of you are attentive. Please be quick in voting your options. So I guess that looking at the responses, I get that most of you, those who are attending the lecture, those who are not simply logged in but not attentive. So there is some 15 to 20% of the students, they would log in and they would not listen to the lecture. So that category of the students would answer it incorrectly. But the others who are listening to this lecture and those who are comprehending it, I don't feel that was a difficult question. Okay. So most of you are answering it correctly, right? About 85% of the students are answering it correctly. So that is good enough. So let me close the poll. Some 70% of the students have voted. Okay, and I'm closing this poll and sharing the results. Okay, so the results are, as you see, that isentropic process means entropy is constant. Okay, so that is the correct answer. That isentropic meaning the entropy is constant. So let me hide this and let me ask another question, okay, which is related to this. So please be quick in recording your responses, because all these responses, they get captured in my GoToWebinar app. So you need to be very quick in responding. So this is about actually a similar sort of question. So sizable students are making mistakes in this. I had explained you this very clearly in this video, in this lecture, that when you are talking about a reversible isothermal process, then the entropy might increase or decrease, okay, depending upon the direction of heat transfer. So if there is a heat transfer to the system, which is isothermal heat transfer, then as is the case of Carnot engine, right, you would find that because along with the heat flows the entropy of the system, of the working fluid, would increase, right, when there is a heat transfer to the system, even if it is a isothermal process, and if it is a heat rejection, if there is a heat rejection, as it happens in the Carnot engine, when there is a heat rejection and the temperature remains constant, okay, uh, there too you will find that the entropy decreases. So when there is heat transfer to the system, I had shown this on a temperature entropy plot with the horizontal lines. Okay, with the horizontal lines, that I had shown clearly that during the isothermal process, it can happen that the entropy would can increase if there is a heat transfer to the system, and the entropy can decrease if there is a heat rejection by the system. Okay, so the correct answer is not which 40% of the students are answering. They are totally wrong in that. Okay, so whatever is the reason why they are not answering it correctly, could be that they are not listening, or they are a bit confused. You will find that 60% of the class has given the correct answer. So let me close down the polls. I find that only 70% of the students have voted. So whatever could be the reason, let me close the poll and show you the correct answers. Right. So the polls are closed and I am sharing the results. So the correct answers are the entropy is constant when the process is reversible adiabatic. Okay. So this you need to clearly remember, and I had also shown this by using a mathematical expression that ds is equal to del q by t. If del q is 0, then ds has to be 0. If ds is 0, it means that s is constant, and s is constant means entropy is constant, and when the entropy is constant, we call it as isoentropy process, that is isentropic process. Okay, so the entropy is constant when the process is reversible and the process is adiabatic. Okay, the meaning of adiabatic means there is no heat exchange, and when there is no heat exchange, there is no heat transfer. There is no heat transfer, then there is no entropy transfer, and because the process is also reversible, so there is no way that the system can have an increase in entropy. So the increase in entropy of the system during a reversible process can happen only via the heat transfer. And if you are not having the heat transfer, then the entropy would remain constant if the process is reversible, right? So a reversible adiabatic process is a process in which the entropy is constant. So let me hide this, the response. Okay. A question, a related question. And this is based on the discussion which we had recently. So I guess that about 60% of the class is getting the correct answer. Another 40% they are still struggling to get this concept. So the poll question is very straightforward. It talks about the entropy decrease, and I had told you that when you are talking about a reversible process, and if there is heat transfer from the system to the surrounding, then from the system to the surrounding, whenever there is heat transfer, the entropy would decrease, and if there is a heat gain by the system, the entropy would increase. Along with the work, there is no flow of entropy. So work is an organized form of energy, and it does not create any disorder when you are transferring the work. Okay, so the work transfer is not associated with either increase in entropy or decrease in entropy. It is basically the heat transfer which is associated with the increase or decrease in entropy. So the students who are saying that work, because the work is done by the system, the entropy would change, they are totally wrong. In no way is the work transfer related to entropy change. This you need to keep in mind, that work transfer is in no way related to entropy change. So let me close the poll and let me share the results with you. Okay, so I'm closing the poll and sharing the results. So as I see that about 65% of the students have answered this question correctly. The entropy would decrease if the heat is lost by the system, closed system. Okay. So let me hide this and let me repeat this once again. Let me rub this all. Okay. So suppose this is a closed system, and suppose there is a heat transfer of 100 there is 100 kilojoules of heat transfer from the surroundings, okay, to the system. So let me ask you one question, that what will happen to the entropy of closed system, and what would happen to the entropy of surrounding? What would happen to the entropy of surroundings? Let me ask you this question. Okay. So I'm asking this question. You can answer it in the questions column. Mohan Deepak. What is the answer for this? I'll be asking you randomly, okay, depending upon, I can also change your attentiveness by this. Okay. So this way. So Yuvraj Chaudhary, can you answer this question? Yuvraj Chaudhary, Rushali, Yugandhara, Sonone. So I'm reading some names: Vivek Chaudhary, Vivek Muka, Rushali, Ugal Mule, Yashraj Chaudhary, Yugandhara Sonone. Okay, of these names which I had called, okay, let me see your responses. What would happen? Om Patel is answering. Still, I am asking you what would happen to the entropy of the closed system, and what would Chinmay and have answered, but I had called some other names, so I'm expecting them to answer also. What would happen to the Atharva Pandit is answering. Okay, Atharva, you are right. But what would happen to the entropy of the surroundings? What would happen to the entropy of the surroundings? Atharva? would increase of the closed system. That is correct. But what would happen to the entropy of the surroundings? Rushali is not there. Rushali, Vivek, Yash More, Yashraj Chaudhary, Yugandhara. Yashraj Chaudhary is answering. Okay. What about others which I call? Okay. Atharva, you are right. Atharva, you are right. Entropy of the surrounding would decrease. Is correct. Fatima. Fatima is the correct name or surrounding constant? No. Your name is Fatima or first name is Fatima? What is your first name? Acha, Ananta. Okay. Am I pronouncing it correctly? Ananta? Okay, thank you. Let me, without going into much detail, okay, right, Kunal, you are right. Your answer is right. See, uh, the now can you see the whiteboard? Can you see the whiteboard? Okay, okay, thank you. So what will happen is when you are transferring the heat from the surrounding to the system, okay, the along with the heat flows the entropy. Okay, so there would be an entropy transfer. There would be an entropy transfer. Okay, from the molecular aspect, from the microscopic aspect, what would happen is when there is a heat flow into the system, the molecular disorder would decrease. Disorder would increase. Okay, would increase. So because of the heat flow, the molecular disorder would increase, and hence the entropy of the closed system would increase. Entropy of the closed system would decrease. Now this heat has to come from the surroundings. So this surrounding is losing the disorder. So the surrounding is losing some disorder. So surroundings is losing certain heat. Okay, it is losing the heat, and this heat, because it is losing the heat, some of the entropy would also be lost. Some of the entropy of the surrounding would also be lost. So the entropy of the surrounding would decrease. Okay, entropy of the surrounding would decrease. Right. So this you need to keep in mind that entropy of the closed system would increase and entropy of the surrounding would decrease. Right. Let me ask you another question. I hope this is clear to you that when there is a heat transfer from the closed system to the surrounding, the entropy of the surrounding would decrease and entropy of the closed system would increase. Okay. So let me now ask you another question. Okay. So let us say this is a closed system. Let us say this is a closed system. This is a closed system. Okay. This is a surrounding. There is a surroundings. And this closed system is a adiabatic system. Adiabatic system. Adiabatic system. Okay. So my question is, what will be the change in entropy? Okay. So what will be the change in entropy of the system during if the system undergoes during the irreversible process? If the system undergoes a irreversible process. Anybody can answer this? It is a closed system. It is an adiabatic system, and this closed system, this fluid in the closed system, uh, is undergoing a certain process. And there is no there is no heat transfer. The heat transfer is zero. The heat transfer is zero. Why is the heat transfer zero? The heat transfer is zero because that is a adiabatic system. It is a adiabatic system. That is a system having an adiabatic wall will does not allow the heat transfer. Does not allow the heat transfer through the wall. Okay. So my question is, what will happen to the entropy of the system during an irreversible process? During an irreversible process. Okay. What will happen to the entropy of the? Oh, sure. Rushali is saying it will remain constant. Ritesh is saying it will remain Vedant is saying it will remain constant. Tejas is saying that it will remain constant. Pranav is saying it is constant. Gautami is saying it will increase. So Gautami, can you answer why it will increase? Gautami Nikam, she is saying that it will increase. Why will it increase, Gautami? Yash More is saying it will remain constant. Ganesh Shikar is saying it will remain constant. I want Gautami to answer. Parikshit will say that it will increase, right? Parikshit. Yeah, Gautami and Parikshit, they are right. Others, Vikas is also right. So please note that some students are listening very attentively. I'm happy about it. Gautami and Parikshit. Sairaj is also correct. Vikas is also correct. See, again remember this, that change in entropy of this closed system, can happen because of two things. So one is change in entropy because of heat transfer. And other is the change in entropy because of irreversibility. Okay, so I had used two terms. One is the entropy transfer because of heat transfer, and other is entropy generation because of irreversibility. Other is the entropy generation because of irreversibility. Now, in our case, we had said that the system is adiabatic. So the heat transfer is zero. So the heat transfer is zero. So the del Q by T reversible is zero. Because this term is zero. The numerator is zero. So first part is zero. So the entropy transfer is zero. Right? So the entropy transfer would not change the entropy of the closed system. Right? However, because of irreversibilities, there would be entropy generation. So the closed system entropy would increase. If the process is a irreversible process, even when the heat transfer is zero. So the correct answer is, which Gautami has answered it correctly, Parikshit has also answered it correctly. So the correct answer is the entropy change during this process, which is the irreversible process, would be positive. It would be positive. That is, the entropy would increase. The delta S would be greater than zero. I hope this is understood. Okay, is this clear? If it is clear, say yes. If it is not clear, if you want me to repeat, you say repeat. Kunal, we are not talking about within the system. We are talking about. Okay, got it. Most of you have got it. Yes, Vedanta has got it. Tejas has got it. Anish Patil has understood this. Samir has also understood. Pranav has understood. Ananta has understood. Sushant Kanade, Vaibhav Deshmukh has understood. All right, dear friends. In the next class, I would take a very interesting discussion. Okay, Rusha has understood. All of you understood. In the next class, I would take a very interesting discussion on what would happen to the entropy of the universe. Okay, what would happen to the entropy of the universe. And that discussion has to do with what is known as principle of, it's known as the entropy principle. Okay, entropy principle. So let me stop here with this discussion, that and I want you to think on this question before you come to the next lecture, that in this case, suppose the entropy of the system increases. Suppose in the previous case, rather, let me just ask you this, and then you stop this lecture. I'll just rub this. Okay, clearing the canvas. Okay, I'm leaving this question to you unanswered. Okay, which can be taken up in the next class. Suppose this is a system. Suppose this is a system, and there is a transfer of heat. There is a transfer of heat from the surroundings, to the system, Okay, so you had said that as an answer, that you said that the entropy of the system entropy, you said it increases. Okay, that is what you said. And why is that so? Because heat is transferred to the system. And you said that the surroundings entropy, you said that the surroundings entropy decreases. Okay, so I want you to think on that what would happen to the, suppose this is the system entropy plus the surrounding entropy, okay, which is nothing but the change in entropy of the universe. Okay, change in entropy of the universe. So my question is what would happen to the entropy of the universe? Because you see that the change in the system entropy is going to increase, and the surroundings entropy would is to decrease. Okay, so the question is what would happen to the entropy of the universe? What would happen to the entropy of the universe? And this we would be discussing in the next class. Okay, think about this and come prepared for the answer. Thank you very much for joining. Bye for now.